So I'm going to answer 3 questions from Friday. The first is number 11, which says to identify the open intervals on which the function is increasing or decreasing. So I'm going to go ahead and use the product rule first. Before I do that, I'm going to rewrite the original function. So first times the derivative of the second. Oh, negative 1/2, not negative 3/2. That's a chain rule, so multiply by the derivative of negative 2x of what's inside. Plus second times derivative of the first. So when I clean this up, I get negative, the 2 and the 2 cancel. I get negative x squared, 16 minus x squared to the negative 1/2, plus 16 minus x squared to the positive 1/2. To factor that, I take out the common factor to the smaller of the two exponents, which is a 16 minus x squared to the negative 1/2 power. That leaves me on this term a negative x squared. And on this term, it leaves me with, when I divide out that to the negative 1/2 power, you have to subtract exponents, so you're going to get 16 minus x squared to the first power. Because when I divide out that to the negative 1/2 power, you keep the same base and subtract exponents. 1/2 minus negative 1/2 is 1. So that ends up being overall, keep going here, let's see, 1 over, because the negative exponent, we're going to move it to the denominator, and then the root because of the 1/2 power, times negative x squared plus a negative x squared is going to be negative 2x squared plus 16. So from here, I think I'm also going to factor out a negative 2 from this. So this will end up being x squared minus 8. So it's undefined at an x of plus or minus 4. So those are critical points because the slope is undefined there. And then it's also undefined at plus or minus root 8. Oh, not undefined, but it's a 0. Because when you tee this up, this will never equal 0. It'll only equal an undefined. This will equal 0 at plus or minus root 8. So we have a positive root 8 and a negative root 8. So if we test in and out of this interval, if I test negative 5, I'm going to get, actually the function doesn't even exist, or the derivative doesn't exist here, because if I plug in a negative 5 back in the original part of the function, negative 5 squared is 25, 16 minus 25 is a negative number, squared negative number can't do. So the same is going to happen when I plug in positive 5. So those aren't even in the domain. While negative 4 is in the domain, it's there's no slope there. So if I try something like negative 3, the derivative is going to give me a positive times a negative times x, 9 minus 8 it would be. 9 minus 8 is a positive. So that's going to give me a negative there. If I plug in a 0, that's going to give me a positive times a negative times a negative. So it's going to be another positive. And then it's going, if I plug in 3, because this is just under 3, just under the square root of 9. So 3 is fair game. So I plug in 3, and I'm going to get a positive times a negative times a positive, which is a negative. So when they ask, identify the open intervals on which the function is increasing, it's increasing from negative 4, increasing from negative 2 root 2 to positive 2 root 2. And it's decreasing from negative 4 to negative 2 root 2. And again, I'm off the screen here, sorry. And again, it's decreasing from negative 2 root 2, a positive 2 root 2. a little rough this morning. Can you tell that I've got children prancing around me all the way up to 4? And I also haven't done math in 3 days. So, there's our increasing, and I'll just check the back of the book, make sure I didn't make a silly mistake. Good, decreasing, perfect. So, maybe that factoring part that we're always concerned with could have come back to help you, but if you want to pause and look at that work right there, you can. Then I'm going to move on to 51. I had 2 questions on 51. And the instructions for 51 were to, just get a copy down here. Let's see. Find the critical numbers, find the intervals where it's increasing or decreasing, apply the first derivative test to identify any relative extrema, and use a graphing utility to confirm your results. Okay, so first find the derivative. The derivative of a log function, 1 over natural log of the base 4 times that, whatever you're taking the log of. Probably would be better if I had it x ln 4. Okay, so this is going to be undefined only when the denominator is 0. So that's going to happen at 0. And I'm actually going to do an open circle there so I know that's undefined. And then when this whole thing equals 0, so when 1 minus 1, when it equals 0, that's another relative, that's another critical point. So I'm going to bring that over, cross multiply, divide by the natural log of 4. So when x equals 1 over the natural log of 4. So that's a positive number. I don't know exactly what it is, but 1 over the natural log of 4. That's 1 point something. 1 over 1 point something is a decimal of some sort. So if I want to check now, I'm not going to need to check anything over here because these numbers are all out of domain, period. The graph doesn't exist here in the negatives because you can't take the log of a negative. But in between here, like let's say if I plugged in, I don't know, what's going to be an easy number to take the log of? 1 over ln of 4 is a decimal, I believe. I don't think it's too small, so, but let's check it before we, 1 over the natural log, turn it off, of 4. I don't know if that's better or worse. 0.7, yeah, so it's a decimal, but it's not too small. So if I plug in 1/4 as a check, oh, I'm not plugging into there anyway, that's right, I'm plugging into here to see if it's positive or negative. So let's plug in like 0.5. So if I plug 0.5 into this derivative, I'm going to get f prime at 0.5 is going to be 1 minus 1 over 0.5 ln of 4. A negative number. So we're decreasing there. And then if I plug in like 1, I'm going to get 1, well, I'll just do it here. 1 minus 1 over the ln of 4. Because 1 times the ln of 4 will just be ln of 4. And I get a positive. So we're decreasing from 0 to 1 over the ln of 4. We're increasing from the 1 over ln of 4 to infinity. And we have a relative minimum right here. And then use a graph to confirm our results. So let's have some fun with this and graph it. I do want that on. Yeah. X minus, I don't ever do log base 4. I use the change of base formula, which is log of x over log of 4. and then zoom, let's check our window, 0 to 10 we'll say, and negative 10 to 10 just because I'm not sure what's going to happen. Okay, so there's a little dip early on, and there we have the relative extrema. If I do second trace and find that relative minimum, also looks like it happens to be the absolute minimum, but that's not what we're being asked about. So, whoops, enter. Enter. It's going to tell us that that's happening at 0.72134701, which, if you remember, was exactly what 1 over the ln of 4 was. 0.721347, and so on. So, find the critical numbers. Got them. Find the open intervals, increasing, decreasing, and apply the first derivative test. And then use a graphing utility. Perfect. And then I had one more on, was it 55? Same set of directions. The function was e to the negative 1 over x minus 2. So this is going to be a chain rule. E to that still times the derivative of what's inside, which will be a quotient rule. Bottom times derivative of the top, which is 0, minus the top times the derivative of the bottom, which is 1, all over bottom squared, which is going to clean up to just being 1 over that. Okay, so this is going to be undefined at 2. It's the only place. So I believe that's the only critical value because this will never equal 0 times this. This will never equal 0 because the numerator is a solid number. And this will never equal 0 because 2.7 to no power, whatever, gives you a 0. So that's our only critical point. So we now need to test something bigger, which would be 3. Now, 2.7 to anything, no matter how positive or negative, is going to be, because even if this gets to be a huge negative number, it's just going to be a really small positive decimal. So this is always going to be positive, so I'm plugging in 3. And 1 over, this is always going to be a positive, so this is always increasing. And since that first part's always positive, and by the way, this is being squared, so that's always going to be 1 over a positive, so that's always going to be increasing. So this has only a critical number at 2. It's increasing from negative infinity to 2, and then again from 2 to infinity. And then there is no relative extrema because it's increasing and then increasing again. And we're going to use a graph to confirm our answers. So clear that guy out, and we're going to do e to the negative 1 divided by x minus 2. So here it's increasing. Yep, and we have an asymptote, it looks like, at 2. So it's increasing, and then it jumps over this asymptote and continues to increase. So we don't have any relative mins or maxes. Let me just double check that. No critical numbers. I called 2 a critical number because it's where it was undefined. I don't know why they're not calling that critical. I think I do remember this from last year. I call anything critical that's worth testing in and around. So if it's undefined there, yes, it's worth testing in and around because it could be an asymptote, and then your behavior could change on the other side. Increasing from negative infinity to 2 and 2 to infinity, and no relative extrema. So we've got all that. All right, so Sorry it came a little late, but there are your answers for Friday's homework, and hope to hear from you today soon. Hope everyone had a great weekend.